Watching other auditors work and learning exactly how they tackle a code base when they first open it and as they continue to go throughout the audit process is absolutely key in leveling up your security game. But oftentimes, unless you manage to join an auditing team, when you're first starting out, it can be pretty hard to get the chance to peek over the shoulder of another auditor and learn from their process. And that is, of course, why I decided to make this series where I live audit a smart contract system for Filecoin alongside one of their research engineers, Denis, who has almost 2 decades of cybersecurity and blockchain experience. In this series, you have all of the context on the smart contract system that I do, and you get to walk alongside Denis and I as we go through this audit and go through my auditing process and uncover as many bugs and vulnerabilities as possible. Last episode, we got a overview of hierarchical consensus from Denis. In this episode, we are ready to dive in and start auditing the smart contracts live. But first, before we begin, of course, my name is Owen, and over a year and a half ago, I founded Guardian Audits, and ever since then, we've uncovered dozens and dozens and dozens of critical and high vulnerabilities. And I've personally spent easily over 1,000 hours, 2,000 hours at this point auditing smart contracts. And my goal with all of these videos that I put out, and especially this series that we're doing here, is to help you overcome everything that I had to learn along the way and basically download that information into your brain so you can become a much, much stronger security engineer, blockchain developer, whatever it is that you're looking to be in a fraction of the time. All right, fantastic. So without further ado, let's get into the second episode of our Filecoin auditing series. Fantastic. We are ready to dive in. So last time we covered hierarchical consensus. Hierarchical consensus is essentially the spec that these smart contracts were designed to uphold. That's why we needed to first understand hierarchical consensus before we could even start to understand what this smart contract system was doing, what it was supposed to achieve, and then to take it one step further and actually go and uncover bugs and vulnerabilities with it. Now we're about to dive in here, and you'll notice as we're going through the contracts, we're using a very particular approach. We aren't just simply jumping around all over the place, just trying to find findings in this file over here, and then going and opening this file and seeing if there's findings over here. But in fact, we're actually enumerating the high-level goals of the system, and then Denis is walking me through the code paths by which each of these high-level goals are achieved. And then as we're doing this high-level walkthrough to get a feeling of the code base and how it achieves these things, instead of digging really deep and getting distracted by the first thing that we notice, we're doing our best to make an initial note and be able to come back to that and verify it later. All right, so without further ado, let us get this audit kicked off. All right, great. So really the first part here that we're going to, like, before we even just start to dive in, I know you already have, like, you already understand the contracts entirely, but of course I don't have like the full understanding of them just yet. So before we just like get our hands dirty and dive in, what we'll do is we want to list out we can literally just type it out at the top of this file, like after the imports. In a comment, we'll just put what are the high level like goals of this system, right? So for this subnet actor contract, we have things like a validator can join, they can, basically add their stake and then ultimately create a subnet, right? So that's one thing. And yeah, the interface, exactly. The interface is perfect here. So we will literally just have join, leave, kill, and then there's this idea of submitting checkpoints and then rewards. So yeah, I mean, literally exactly this interface. Contracts are not always as nice as this with the interface, where the interface is literally all of the like jobs to be done of the system, but this is perfect. So what we'll do first is let's essentially follow the path for what does it look like when a validator is like joining a subnet. And then, so what we'll do is we'll go to the implementation of the join on the subnet actor. And yeah, let's just literally, we'll just walk through join and see what is happening here. So I guess the way we can do this is, I guess you can sort of like do like just walk me through the code, and then as we see stuff, as I see stuff that I want to note down, I'll just like call it out, and then we can leave it as like a note in the code, and then we will come back to it and dig into it further after we've gone through all of these high level jobs to be done.
Yeah. Okay. So to connect to the subnet, there are three commands: join, leave, and kill. And the process for a validator started using join command. So there is a subnet, and I, as a user, have a validator, and I want to join this subnet using my validator. And to join a subnet, I have to stake some tokens, right? Because we are in proof of stake system. And this stake will be used to punish me if my validator is misbehaving. So when I want to join validate subnet, I should send my collateral value in a transaction, in the message, right? And the contract stores it in a stake mapping, right? It also counts the total stake for the subnet, and this is the logic. This is the logic related to should we run that network? Do we have enough collateral to start it or not? Or maybe we have already started that network. Is it active? And in that case, we don't need to create a new one subnet. We don't need to register a new one subnet in the gateway actor, and we just can count our stake, count the stake of the joint validator, and that's it. And this statement does exactly that. So yeah, and we also should note here that mean activation collateral is a parameter. When we create the subnet, it's parameterizable, and the subnet committee can provide different parameters in contract. So it's a subnet policy. It's defined by the users. So what we do here is we check consensus. There are several types of consensus, and the delegated is a special case because in that case there is only one validator actually. So only that validator will propose blocks. Because of that, we need to check that. Then if this validator is already in validator set, then we don't need to add this validator, of course, right? We require that the stake of the sender should be more than min activation collateral. In this case, we add validator in our validator set, and we should note that validators is a enumerable set. I believe that's important here for further analysis. Yeah, and here we check the status of the network of the subnet. If the status is just instantiated, so it's not active, then we should call register function in the gateway.
Got it. And instantiated is like the initial status when this first gets deployed.
Just created it. It's not active. It does not have enough validators, or it doesn't have enough collateral value to activate it, and we just need to continue to get more validators.
Yeah, you said something interesting there. Actually, is there's two conditions for it being activated, right? You mentioned the collateral, which is what we're checking here with total stake is greater than or equal to the min activation collateral, but then also the number of validators, right? And something I was initially interested by in this function is it possible to, since we're checking the total stake against the min activation collateral, and we're checking each individual validator against this min activation collateral, is it possible to, and maybe it's fine to, this could be just like a note that we leave and come back to, is it possible to have a subnet that is registered in the gateway even though we don't have any validators? So what I mean by that is, like, let's say I had one validator come in and send min activation collateral divided by 2 so that they're not added to the validators set here, but then we have a second validator come in and add another min activation collateral divided by 2 so that the total stake is now the min activation collateral, but we have no actual validators that have breached that threshold of the minimum. And so we go to register this in the gateway, and we'll see what that register function does in a second. But when we do that, we might not have validators in that set, right?
But is it possible, because here we check that the stake, the senders should send more than min activation collateral, so it's not possible to send half of collateral.
Well, we only add them to the set in that case, right?
Yeah.
So
right.
it is possible to call this function with a message.value that's like half of the min activation collateral, right?
All right.
And then in that case, if I send that exact message.value that puts the total stake variable over that lower threshold of the min activation collateral, then at that point we will call that function on the gateway, right?
Mm-hmm.
But there's no sort of guarantee that any validators have been added to the validator set, right?
Can you provide concrete?
Yeah, absolutely. So what we'll think about is, like, let's think about like a base case of this subnet actor contract has just been deployed, right? There's no validators yet, and it has not been registered yet in the gateway contract. So what we'll sort of envision in this scenario is, if let's say we have two validators, or let's just say two addresses.
Okay.
Right. And the first address sends, let's say, a message.value of 5. And let's say the min activation collateral is 10, right? So 10 ether or whatever for the min activation, but I only sent 5. Okay. So if we walk through one by one, then the stake, what is the value of the stake mapping for this one address?
Yeah, so in this case, we don't add validator into validator set, right?
Yeah.
And in min activation collateral is 5, right?
That's 10.
10. Okay. 10 and total stake is 0. So we don't call register. So
Yes.
we totally ignore this if statement, and we call just add stake. So we just call add stake, but we did not add validator into validator set.
Yes. So now let's think about what the next address does. Now the next address comes and they send a message.value of another 5 ether.
Yeah. Now I see. Yes. Yeah. So in this case, and the second, let's say 7, right?
Yeah, exactly.
7. We will not add validator in the validator set, and total stake is still 0. So we will increase the stake in the gateway actor, but and here, because total stake will be 10, and we call register. Yeah, that's correct. So that's interesting case. So probably there is a
yeah, exactly. So this is something that, like, while I'm initially going through this function, something that I would just like write a note on because like I don't fully understand what the register function is doing and what even the implications of this would be. But it's something that I would just write. So we can write like a comment. We can say like at audit, just to note this is something we want to remember, something to come back to, and we can just say, yeah, exactly, that's perfect. We can say anything to remind us of this edge case, right? So I would say, like, what if we have two addresses that had like funded this enough to reach the min activation collateral, but none of them were added as validators, or in so many words. Yeah, perfect. And then basically the idea with this is that we don't want to dig into this too far and get like completely off track, while we really still just need to understand, or I need to understand the system more to know, like, is that a problem? Is that totally expected behavior? Or, how much of a problem could it be? So we'll just leave that note. And then after we understand more, then we can come back to things like this and start to dig into it a little deeper. The next thing we'll want to look at is these like register and add stake functions, right? In the gateway.
Yeah. Okay. So the description of the register is here, called by subnet actors to put the required collateral and register the subnet to the hierarchy. Maybe we should note that subnet actor is implemented by the subnet users, and gateway actor is implemented by the provider, by the APC owners.
Okay. Now we're interfacing with that gateway, and we're sort of trying to connect this subnet, right? They just basically register in the system, right?
So we are in register now. So a register function is external, payable, and we can see that it can be called by everyone. In reality, it's called by a subnet actor. There is a misprint here. Threshold stake. Okay, so min stake is a parameter, not parameter. It's a state variable. No, it's a parameter. So it's a minimum stake that should be enough to send from a joint validator. So
yeah, and does that correspond at all to the minimum staking amount in the subnet actor?
Yeah, exactly.
Okay. One thing I am thinking, if we quickly just go back to the subnet actor, maybe another note we might want to leave is that I noticed so we have this min activation collateral. Okay. And we're sending the total stake.
So it's not. So it's total stake. Yeah, it's not
got it.
A value from the message.
Yeah, not just the message value. So yeah, that was one thing that I thought might be an issue, but no, we're actually doing that perfectly fine. So that's great.
Yeah. So we create. So if the total stake is the current stake is enough, we create a subnet with a messenger with ID equal to sender address, and then we all get subnet by that ID. And if we have already created it, in this case the registered variable will be true, then we just revert because we already have that subnet.
Yeah.
Otherwise, we update their values. So we fill subnet values, subnet parameters, right?
Yeah, exactly. So this is like the initialization.
Yeah, and here we set status to status active, all right? And also we create a genesis epoch equal to the block where we register this subnet. And we increase state variable total subnets by 1. So total subnets. So we should note here that there is in each replicated state on a network, there is only one gateway actor, but can be many different subnets. So in this case, right, we should increase the total number of subnets by 1 because we register.
Got it. So the gateway can register like
many different subnets.
Yeah. Okay, great. One thing I am noticing that we might also want to note is that there's a status for the subnet in the gateway, and then there's also a status for the subnet in the subnet actor contract, right?
Yeah, they're different.
Yeah, so these are basically meant to indicate, they mean different things depending on the contract, right? I wonder, so is there any sort of intersection between the two statuses where if we were to make, one status active on the gateway and then the subnet actor thinks that it's still like instantiated, would that potentially cause like an issue, something like that? That's just an initial thought I'm having, something we might leave like a note for to come back to and sort of validate further. Okay, perfect. And then the next thing is, so I see we like create a subnet ID, and that's based on the message.sender. Let's just, without getting like too deep in the details, just get an idea of, I believe you guys have like a path sort of system for creating IDs where the message.sender here is like appended to a path to get an ID that is like a unique route to this subnet or something like this, right?
Mm-hmm. Yeah, correct.
Okay, so we'll just quickly dive into that. We don't have to go too deep into like the innards, but yeah, we'll just look over this briefly. Okay, so so this is interesting. So the subnet so we have this new subnet, and we basically say that there's this parent subnet, it looks like, right? So we have the subnet, and then the actor it's like you take the previous like parent subnet and you just append the actor onto it. So that's cool. One very minor thing that I'm initially thinking is some gas optimization where first of all we're assigning the default value for I and then also the length of the root. Maybe that might have been a conscious decision that the LimeChain team made is, perhaps it's actually more optimal to when you have less like a less deep array of subnets, it might be more optimal to compute the length right there when you're not doing as many iterations compared to caching the length of that. But something I'm noting, just something I'm thinking of initially. But besides that, this looks good. I think the idea of like having like this root for an ID, that's pretty cool. It lends itself well to the structure. So that's cool. And then I imagine you guys have to hash this or something when you want to use it in like a mapping or something like that.
For route or what do you mean hash of?
You like the ID or something like this. Yeah, exactly. Like we have this 2-hash function right there. The subnet ID, we ABI.encode it and then we hash it on like line 46 there.
There is a 2-hash function. Yes, the team decided to use hashing to compare different names. Yeah, but
Got it.
that decision probably will be reconsidered later because maybe worse to compare just bytes.
Yeah, that makes sense. Okay, so I think we have a pretty good idea of like registering what that looks like. Basically, we start in the subnet actor contract, and then depending on if we've accrued enough stake in the subnet actor contract, then we come in and we actually call the gateway and we register it in the gateway system and actually take the money there and send it over the gateway. I think that's something I do want to note. Just keep in mind is that we do have funds that are like intermediately sitting within the subnet actor contract, and only once we've accrued enough funds, then we send those over to the gateway. And so I think the next thing we can look at is we can start off and look at how leaving works.
Okay, so leave, the goal of this function is to change the state of the subnet if a validator has decided to leave subnet for any reason. So what we're going to check? So if the stake of the message sender is 0, then not validator. I would say that here it's not explicit check, right? It's implicit check. The explicit check would be to use validator set. But
I think that's fine in this case, since the way the enumerable set will work is if we remove it, it's sort of idempotent, right? Where even if we remove them and they're not in the mapping, it just won't do anything.
Yeah. So when a validator is leaving, we should send the collateral value to that validator. So we get the staked amount and decrease the total stake by that value. Remove this validator from the validator set, and then we call release stake on gateway actor and send value to that validator, and we see that must be non-reentrant, not killed. So I believe we should check these modifiers because some logic is used in this validation.
Yeah, absolutely. Yeah, so I think we know what non-reentrant does. Next, I'm guessing, so signable only, is that one of those like only EOA checks where we check like the code at an address or something like this?
So signable only. Yeah.
Okay.
Actually, that's interesting one because so this is actor in Solidity, but these actors will be running non on EVM, non on Ethereum virtual machine, but on Filecoin virtual machine.
Yeah, it's a little bit different.
And in this case, that's important because there is no, I would say, correct way to check whether that account is a user account or external account in Ethereum virtual machine term or a contract. And that's kind of a heuristic function. I would say we believe it works on for Filecoin virtual machine, but the current state is that there is no robust way to distinguish between account or user account and contract on Filecoin virtual machine. And I believe that's a crucial thing for reentrancy, attackers, and so on. So we should keep it in mind.
Yeah, one thing I want to ask is what's the need to ensure that it is an EOA versus a contract calling?
For example, because when we can check reward function. So in this case, when we send value to validators, maybe that's a contract, maybe that's a user account. And in that case, it just can revert. And this reward function to reward all validators will be just revert, right?
Okay, great. I think, yeah, this is definitely something we will want to dig into. I think as, personal preference, I always sort of had like a code smell or whatever, however you put it, when these like only EOA checks are used. Personally, I would say a better approach might be to, instead of like pushing the reward amount directly to the contract or the validators, then like all of a sudden, now that we're pushing this value to that address, now we have to care whether or not there's a contract there, right? But instead, if we flipped it and we made like a mapping where we just say, this validator has this much ether that's claimable that they can then come and claim later, then now we don't need to care if it's an EOA or if it's a contract, right? Because we're just never going to call it. And also, so I'm not exactly, I don't have all the context on the Filecoin, the way that Filecoin manages, EOAs versus contracts. But like you said, there's no like robust way to like definitively say, and also we don't know, like in the pure EVM case, you could always have a contract that might pass that external code size check. It might even pass it in the beginning of a transaction, but then later on in the transaction, there might actually be a contract there. So it's not a foolproof way, and there are ways around it. So yeah, personally, one thing that I might do instead is pull over push exactly. And then that way we don't need to worry about like checking if it's a contract or things like this.
Yeah, but that was just an example how it can extend the attack surface. We can just keep it in mind and illustrate the attack vectors later.
Yeah, absolutely.
Okay, so we were discussing modifiers. So signable only, it's checked that the holder is a user account. Not killed is about the current status of the subnet, and so we check that the status is not terminating and killed. So if it's killed, then we revert.
Yeah, it makes sense.
Yeah, and from my perspective, I would add that so when we see not killed, then but in reality we see that we check that status is not equal to terminating and killed. I would call that function, that modifier, differently. I would say not killed or terminating or something like that, because there is a minor inconsistencies.
Yeah, to be more explicit. Yeah, I could see that. Yeah, that will be important to note as we continue to see the modifier. Do they ever think that it is just killed? And it would be terrible if I put that modifier on a function that needed to like make the switch from terminating to killed. So yeah, that's a great thing to note. Something that could easily be slipped up.
Okay, and not killed, and mutate state is used for all three methods: kill, leave, and join. And actually, this is very bad approach, because here we change the state. So it's not just a check when we check and revert or something, or not revert, but here we change the state depending on the current state. So mutate state implement the state machine. And if we started talking about potential reentrancy attacks, then now if we don't know the code behind mutate state, then and we are trying to analyze this code, whether it correct sense of reentrancy attack, then it's fine, right? Because the effects section is here and then just the call sections. But in reality, there is effect sections also in mutate state, and that's important.
Yeah, I agree. I think that's especially important because, well, so I don't yet understand what depends on the status of the subnet actor contract. But if there is, let's say there was another contract that read the status of subnet actor and depended on whether or not the subnet actor was live or, instantiated or killed or something like this. If now on line 213, if I, as the message.sender, get control over the transaction before that mutate state actually happens, can I go and interact with that other contract, which relies on the status of this one, and manipulate it in some way because that mutate state hasn't yet taken advantage? So yeah, that's a fantastic point. It could lead to like a read-only reentrancy or, even something potentially worse. Another thing that I'm thinking is I actually don't remember what the exact execution of these modifiers are when they're spread out, whether it's left to right or right to left. But I'm wondering if, that non-reentrant, the way that will work is we have a flag that is checked before, and then we say, okay, now we're entered, and then we set the entered flag to false at the end of non-reentrant. I'm wondering in these modifiers how that will work, but I don't think it shouldn't matter because we don't make any external calls in any of these modifiers, so we should be fine there. But yeah, so I think that should be fine, but something to note.
But don't we call the function here because message sender can be...
Yeah, this one is a potential issue. I was thinking more of if it would be a really interesting attack vector if, let's say, in mutate state, in that modifier, in that code, let's say at the end of that mutate state modifier, we actually made an external call. Then at this point, I think this is the ordering. I don't remember exactly, but in the non-reentrant modifier, after that modifier, finishes, we've set the reentered state back to like not entered, right? So potentially, if you did, for whatever reason, make an external call at the end of mutate, you could actually re-enter into the contract and non-reentrant would not apply since we're making that call at the end of mutate state. But that doesn't matter because we aren't making any external calls in mutate state. But that would be a really cool exploit if there was a modifier that did make an external call like that.
Okay, but so we should not remove non-reentrant modifier here, right?
Yeah, we should definitely keep non-reentrant. It's there's nothing wrong with it at present. Just if there was like an external call in mutate state, we might be able to like circumvent non-reentrant because like I think we could just click into non-reentrant and just look at the implementation of that really quick. Yeah, so like what I'm thinking is possible is if what we do, we have that non-reentrant after call on line 340, then we set the status to not entered, right? And then now when everything is not entered, now I can magically call any one of those non-reentrant functions again in the same transaction, as long as I have some piece of code that is making an external call after that non-reentrant modifier is finished executing, right? So the only way we would be able to make an external call after that is if we were in the mutate modifier and we were making an external call like at the end of the mutate modifier. But of course, we're not actually doing that here.
Yep. And okay, so now we should go to release state, right?
Yeah, absolutely.
Yep. So the description is this wise: recover some collateral of the subnet and release state. So if we call this function with the amount that we should send to the leaving validators. If it's 0, then we get the target subnet, check that this subnet is registered, check that the subnet stake is less than the more than amount, right? Decrease the subnet stake. If the subnet stake is less than minimal stake, then we change the status. The subnet becomes inactive, and we send value to the actor. So we get the actor for that subnet, and send it to that actor.
Got it. So this is sort of like the withdrawal from the gateway to the subnet actor, and then the subnet actor takes that stake amount and sends it right back to the validator.
Yeah, so we send it to the subnet actor, and then the subnet actor send it to the leaving validator.
Got it. So one thing that I remember from when we were registering is we incremented like the number of subnets, right? And then that was only when we like activated it. Now I'm wondering, does it matter if when we now go below the min stake?
No, because the subnet still exists. It just becomes inactive. We decrease the number of subnets in kill.
Okay, perfect. So that subnet is still like quote unquote in the gateway system. It just has to be, it has to get more stake. So now I'm wondering just quickly if we were to now add stake to this subnet, I guess we could expand the function right above and just look at that. If we add stake again and it goes above this threshold, do we now activate it?
We activated this. So to activate, we would call join.
So we would have to call register, right, to be able to get this subnet back to be active, right?
Yeah. I just wondering, is it possible to call it directly? And what if we call it direct without?
Yeah, exactly.
But it's not possible because here. So this is actually implicit access control. Because if we just call it, then we get the non-existent subnet or just an empty subnet, but not the target subnet.
Yeah, exactly.
Because of that, we must do operations like join, add stake, and so on through the subnet.
Yeah, that's a good point.
So we call join, and here, because it's so here the status inactive, right? So the status is active, and because of that, we call this. If we join, if a new validator join, then it calls add stake, right, on the gateway actor, and the subnet the stake will be increased.
Yeah, so the thing I'm thinking of, does there need to be that reflective check?
But the status will not be changed.
Yeah, that's exactly what I'm thinking as well.
Yeah, that's I believe that's if it's true, then that this is very good. So if a validator gives subnet and subnet and this.
Okay, awesome. Yeah, that's a great note. All right, that is all for this time. We got a good handful of great initial findings, and we got a really good handle on this code base to begin with. So in the next episode, we're going to start to go over a few different areas of the code base and start to dig in deeper and uncover some more interesting findings that are a little bit deeper inside this protocol. Can't wait for you guys to dig into episode 3. And of course, I hope that you enjoyed episode 2 here and you got a few key takeaways. In fact, if you had a few key takeaways, you had a finding that you thought was really cool, that, maybe something you noticed that we didn't notice when we were going through, put that in the comments below. I want to know. I think the team at Protocol Labs will want to know if you found something that we didn't uncover. That will be extremely helpful for them as well. And of course, if you are on a team building a really cool new breakthrough DeFi application and you're coming up on launch and you're starting to think about security, then I want to know about your protocol. In fact, I would love to do a first pass, completely free review of the code base just to get a set of initial security notes, things you might want to look out for, things that might want to be addressed before you go into a real smart contract audit. And so you can get these free first pass notes when you submit a application on guardianaudits.com/quote. And of course, if you happen to know any other teams looking for a smart contract audit, then of course, send them over to guardianaudits.com/quote. And of course, if you are just getting into security research and you're interested in learning more and even connecting with others who are also interested in learning about the same thing, then go ahead and head on over to lab.guardianaudits.com and apply to join our community of growing auditors and security engineers and people who are just interested in Web3 security in general, and get the chance to connect with people from across the world, learn from others, and even potentially team up with others in our community to complete real audits with real code bases and even get rewarded for your findings and get to produce a real report that has your name on it, something you can show off to others in the space. All right, but of course, that is all for this time. I cannot wait to see you in the next one.